welcome to NPTEL MOOC on fiber optic communication systems and techniques. We were discussing in the previous module the concept of a mode, and then I indicated at the end of the module that we are going to look at a systematic procedure to understand these waveguide modes. Okay. There are a couple of assumptions that one talks about or one makes when we start understanding the modes of a waveguide. The waveguide mode or the waveguide structure is assumed to be uniform along the z axis, okay, and the cross section could be any irregular cross section, but the cross section would remain the same along the z axis. So, that is what we mean by when we say that the waveguide is uniform along the cross section. For simpler treatments, we will also neglect any material losses. So, all of the materials that our waveguides are made out of are considered to be lossless. These two assumptions are of course very unrealistic, because you have in many situations a requirement that your waveguide needs to be bent around. Okay. For example, in integrated optics you may want to connect your input to multiple outputs. So, in which case it is necessary that you use couplers, and those couplers have to be spatially separated by bending appropriately at appropriate angles. Bending of the waveguide at appropriate angles. So, clearly this assumption is unrealistic, but it is sufficient for us to actually that assumption what we use in understanding the modes of a waveguide is because it is mathematical simplicity. So, we do not want to complicate our analysis by allowing the waveguide to be non-uniform. Moreover, we do not want to allow the cross sectional variations that naturally occur when you manufacture a fiber or fabricate a waveguide to actually cloud our understanding of the fundamental transmission problems. So, purely for mathematical simplicity, we are going to neglect any of the non-uniformities that might appear, and for the same reason we are also going to neglect the losses. Okay. If you take advanced courses in waveguides, you would know how to incorporate the non-uniform waveguide structure as well as losses and many other things that you may not really like to consider in the practical waveguide. Anyway, so the idea here is that I have a waveguide of some arbitrary cross section, okay, and this cross section remains the same as I go along the z axis, which is the direction in which the waveguide modes are assumed to be propagating, okay, and this cross section, although I have shown it to be very irregular, remains consistent at all points. So, I mean hopefully this cross section is the same as this cross section, although the figure may not really show it, but the cross section remaining uniform is a key which allows us to forget about the z part, because I can then express all of the z variation simply by writing this as e power j k z z, okay, k z z as the propagating factor along the z, and then focus my attention to obtain f of x comma y for the rectangular waveguides, or f of r comma phi for a circular waveguide, or in general f of u comma v for a general cross section or general coordinates u v and w. So, these f of u v or f of x y, appropriately f of r phi, are called as the modes of the waveguide, and this is the mode that we are trying to find out. Okay. So, modes of the waveguide, this is called as modal analysis. So, the procedure that we are going to follow to obtain this f of u comma v or f of r comma phi or f of x comma y is called as modal analysis of the waveguide. So, did you understand why we removed any z axis from our discussion, or rather we assumed z axis discussion to be in the form of e power minus j k z z? Because we have assumed the waveguide to be uniform along z axis and mode propagating along z axis. So, mode propagates along z axis. Okay. So, what is the systematic procedure? Well, the procedure seems to be quite straight, or is actually straight, not really complicated, but of course, the actual calculations may become tedious and complicated, because if you allow for very general cross sections to consider. Okay. The idea here is that I know that electric field actually has two components, right. So, I have what is called as a transverse component and then I have what is called as a parallel component. The parallel component is the component that would be along the z axis for the case that we are considering, or in general it would be the component that would be along the direction in which the waveguide itself is extended. Okay. And this E t corresponds to the transverse components, that is components which are in the plane that is transverse to the direction of the waveguide. So, in the general case u v are the transverse coordinates, w is the parallel or the longitudinal coordinates. So, E t will be a vector in the u and v plane, whereas having components u and v, and E parallel will be a component that would be along w direction. Of course, it is important to realize that the transverse component could be function of all three coordinates, right. So, it is not necessary that the transverse coordinate be a function only of u and v. Of course, this coordinate dependence is on the w axis is what we have captured by writing as e power minus j k w times w. So, we do allow for dependence on w, but we impose a specific dependence on w in the form of travelling wave. So, all the components that are there as the electric field and the magnetic fields can have transverse components or can be separated into transverse components and the longitudinal component, and each of those transverse components and the longitudinal component by themselves can be a function of all three coordinates u, v and w, but along w, which is the direction of the waveguide, we impose a very specific functional form which is e power minus j k w times w. Okay. If you are confused by u v w, you can replace u v w by x y z and work with planar cross sections to simplify your understanding, but it is not really necessary to think always of the Cartesian coordinate system, right. The electric field we have decomposed into transverse and parallel components. We will similarly decompose H fields also as transverse and parallel components with the same remarks that go with the electric field. So, the first step is to understand that you have E and H and then choose a coordinate system, okay, in such a way that your life becomes simple. For example, if the waveguide happens to be an optical fiber which as such has a circular cross section, then choosing a coordinate system x, y, z will be a very big problem for you, because the analysis becomes very difficult as x and y components couple to give rise to r and phi components, or rather the components E x and E y will be in a very complicated manner depend on x y itself if you were to analyze them in the circular cross section. So, it is always better to choose a coordinate system in which the analysis actually becomes quite simple. Okay. That itself is an art, but luckily we have had a literature of about 100 years to guide us. So, we do have standard coordinate systems, and if your problem happens to be not falling into any of the standard coordinate systems, then good luck to you. Well, there are ways to get around that problem, but that is not our concern here. So, the first step would be to choose a coordinate system which is simpler for you to work. In this course, we will either be looking at x, y, z coordinate system, which is the Cartesian rectangular coordinate system, or we will be looking at r, phi and z, which is the circular cylindrical coordinate system. The second step is that, remember, we have decomposed our electric field and magnetic fields into those E t and H t, E parallel and H parallel components, correct. So, now what we do is we express those transverse fields in terms of parallel components. It is in fact possible to do so by applying Maxwell's equations. So, express E t and H t as functions of E parallel and H parallel, okay, that is longitudinal components. The reason for this is again mathematical simplicity. There is no specific reason as to pick only the horizontal components or the longitudinal components. You could have done the other way around as well, but it is a simplified, this analysis or this method simplifies the problem. Okay. So, that is the second step. So, I express E t and H t as functions of E parallel and H parallel using Maxwell's equations. So, whatever the coordinate system that I have chosen, in that coordinate system I have to express Maxwell's equations and then write E t and H t as functions of both E parallel and H parallel. In general, they will be functions of both E parallel and H parallel. The third step is an interesting step which essentially means or which essentially calls for you to obtain and solve a wave equation. Remember, these are all waves, right, except that the wave is not uniform, it is a non-uniform wave having certain x and y dependence or certain u and v dependence, but it is your responsibility to obtain and solve wave equation for E parallel and H parallel. Usually the functional form of the wave equation will be same for both longitudinal components. Therefore, if you solve one, you can easily guess the solution of the other. There will be some constants of solution which you will have to fix by applying the boundary condition. Okay. So, apply boundary condition to determine the propagation constant. Remember, one of the goals of your analysis would be to actually determine the propagation constant kz, or in general the propagation constant kw. Okay. Of course, you will also have the perpendicular or the transverse wave number kt. Kw will be function of the transverse wave number kt and whatever the medium k vector that is there, right. Anyway, but you need to apply a boundary condition to actually determine these quantities, the longitudinal propagation constant. So, I will just write this as kw, okay, and this corresponds to the propagation constant, or I could have written it as k parallel. Okay. The fifth step is to obtain the transverse and the transverse electric and magnetic field components Et and Ht in terms of E parallel and H parallel. Okay. We have already written Et and Ht in terms of this, but once I know the solution for E parallel and H parallel by following this 4-step procedure, the 5th step procedure is to go back to this step and then obtain the solutions. Okay. These solutions of course have to satisfy boundary conditions as well, and this will allow us to obtain that transverse mode form f of u and v. Okay. So, this 5-step procedure is what we are going to follow in the next few modules to understand different waveguides. Of course, our understanding of waveguides is for slab waveguides, which we have already seen, not really in this using the systematic procedure, but using a big picture of the ray approach. We will see that this approach also gives the same results, and of course, this approach gives you much more information. In the ray approach, you will not know what is the way in which the fields are distributed, whereas this one will allow you to know what the fields are distributed. Ray function, ray theory does not tell you the evanescent fields exist, but this theory will easily give you the evanescent fields that exist and the functional form of that as well. So, there is lot of merit in following this procedure, and for optical fiber analysis the simple ray approach is not satisfactory. So, you need to understand this systematic procedure to derive those mode fields of a mode fields of the waveguide modes of an optical fiber. Okay. So, we are going to look at this systematic procedure, and before I look at it for the slab waveguides and the optical fibers in the next modules, what I am going to do is to reconsider the parallel plate waveguide, okay, which consisted of 2 perfect electric fields, right, and then see how far I can go with these steps to solve and obtain the corresponding electric fields and the magnetic fields, the total electric and the magnetic fields, or essentially do a modal analysis of this particular problem. So, here I can be little careful in choosing the coordinate system. I do not want to work with negative values of x, or rather x equal to minus h I do not want to put in. I will put x equal to h and x equal to 0. Okay. This of course will be the z axis. Luckily for me, u is x, v no need to be considered, and w is z. So, the first step of choosing the coordinate system I have already done it. This is the z direction, this is the x direction. Okay. So, this is how the x direction is and this is how the z direction is. I have also assumed the uniform lossless property, so that the cross section at any time is actually nice plane or a line here, and this height would not change. So, this height of x equal to h, the height of h will not change as you move along the z direction. So, the first step is done, choosing the coordinate system. The second step, of course, while choosing the coordinate system, I have also assumed e power minus j k z times z dependence, with k z being the unknown quantity that I need to determine Remember that was the idea of step number 4. So, we have not reached step 4. I am not going to fully solve this case, I am going to leave most of it as an exercise to you. I will just indicate the procedure. I want to use this procedure to solve for the case of a slab waveguide in the next module. Okay. So, these are basically indicative of what we are going to do, but the full use of the systematic procedure will not be for this one, but it would be for the slab waveguide. Okay. So, first step is to choose the coordinate system, which we have done, and along with that we have also put down the way in which these fields depend on z, which is in the form of e power minus j kz times z. Now, the second step would be to express the transverse components, which are Ex, Ey, Hx and Hy as functions of Ez and Hz. Remember, these are the components that I have, the longitudinal components Ez and Hz. Okay. To do that one, I need to apply Maxwell's equation. The equations that I am going to use are the curl equations. These are the ones that will allow me to interconnect electric and magnetic field. In the case of a free space medium that I am considering between the two parallel plate between the parallel perfect electric conducting surfaces, this would be the curl expression and this would be the expression for H. No current exists in between, therefore, this is simply j omega epsilon naught. I am also assuming that the medium in between the parallel plate waveguide is a free space medium. So, what I get is this expression, correct. This is in the frequency domain or the time harmonic expressions. Now, what is curl of E? Curl of E is basically obtained by obtaining the determinant of this matrix, which will be Ex, Ey and Ez, right, and obtain the determinant of this one, that would be x hat del Ez by del y minus del Ey by del z minus y hat del Ez by del x. Since I am going to anyway take the minus sign later on, so I can actually rewrite this as del Ex by del z minus del Ez by del x. The z component of this field will be del Ey by del x minus del Ex by del y. Okay. This should be equal to minus j omega mu naught x hat Hx minus j omega mu naught y hat Hy and then minus j omega mu naught z hat Hz. Okay. I do not really have time to carry on this analysis in this module. So, what I am going to do is to take this step in the next module. Okay. It is not, the problem is not finished, because we are just at the point of solving the step number 2, where we are trying to express the transverse field components, but these expressions will also be useful for us to discuss the slab waveguide, which we are going to do it in the next module. So, we are going to use the systematic procedure to complete the problem for the parallel plate waveguide and then use the same expressions to see how we can obtain the modal solutions for the slab waveguide as well. Thank you very much.